Warning: the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video and the next few videos are focused on solving, or a review of solving, nonlinear inequalities. This one will focus on solving quadratic inequalities, and this review is meant for those who are enrolled in a college algebra course or a pre-calculus course. Generally speaking, you don't focus a lot of your time or efforts in intermediate algebra on solving inequalities. And the same kind of holds true, honestly, for college algebra and pre-calculus. I would love to say that inequalities occur all the time as you move forward, but that is actually not true. So the amount of time that we dedicate to reviewing solving inequalities like this is going to be somewhat minimal, but some of the concepts here are very, very important as you move through mathematics. Maybe not the solving the inequalities part, but how we solve the inequalities is going to be very important. So let's take a look at our one and only example of solving a quadratic inequality. In another video, we'll solve rational inequalities, and yet in another video, we're going to solve absolute value inequalities. But focusing on this one, this is called a triple-sided inequality. Whenever you see a triple-sided inequality like this, it really is two different problems. You have a quadratic expression here, 4x squared minus 8x plus 3, and it simultaneously has to be greater than or equal to 1 and less than 5. So you solve both of these inequalities separately and take the intersections of their solutions. Now let me say that again. You solve both of these separately, and let's just pretend for a second here that when you solve this first inequality, you get a solution set of x values that are, let's just pretend, strictly greater than some number. I don't really care what the number is. Let's say it's 5. And when you solve the second inequality, let's pretend that you get a series of numbers and they're all less than, again, let's just pretend, 10. So you need your solutions to be greater than or equal to 5 and simultaneously strictly less than 10. The overlap of these regions would be the interval from 5 to 10. So that's the idea as you move forward of solving inequalities, especially compound inequalities like this, which this, like I said, is a triple-sided inequality. You want to take the overlap or the intersection of their solution sets. Now that that is out of the way, let's talk about how you solve these. There are two methods to solve a quadratic inequality. One is used by most students and instructors, and the other one is a method that a few of us use, but it's really meant to reinforce a different skill. So let's go ahead and start with the most common method, which is using sign charts. And we'll apply this method to both the first and the second inequality. So how do you use sign charts for this? The very first thing you do, in both cases actually, is isolate the quadratic expression. That is, move everything to one side. Get this inequality to be some quadratic is greater than or equal to 0. Now that we have moved everything to one side, we can go ahead and start doing what we've been trained to do, which is factor and factor out GCFs, all that fun stuff. Notice in this case, I went ahead and divided both sides by 2. That's a very dangerous move actually when you're dealing with inequalities, because if I had divided by, let's pretend, -2, that inequality sign right there would flip. So just be aware, if you're going to divide or multiply an inequality or both sides of an inequality by a number, make sure that you flip the inequality sign if the number you're multiplying or dividing by is negative. We now take a look at the quadratic expression we're left with, and we hope that we can factor that. I'll tell you right now that likely is not factorable. And I can see that it's not. Two numbers that multiply to 2x squared would be 2x and x. And then two numbers that multiply to 1 would be 1 and 1. But if you were to multiply or distribute out this binomial, you would get 2x squared, and then you'd get a 2x and a 1x and then a 1. And while the 2x squared and the 1 work perfectly fine, the 2x and the 1x can never combine to become a negative 4x. So we have to go back to the drawing board. And when you go back to the drawing board, you're just really asking yourself, when is this going to equal 0? Because you want that baseline of when is it going to be that left-hand side, which is 0. And the easiest way to do that is to use now the quadratic formula. And I wrote it as a little note there. That's really what you're asking yourself. What will make that quadratic expression 0? And of course, we would use the quadratic formula like I just said. And we all know the quadratic formula is the opposite of b plus or minus that b being squared minus 4ac all over 2a. We get down to there, and that simplifies even further. So I can see that this quadratic right here will become 0 when x is equal to 1 plus root 2 over 2 and 1 minus root 2 over 2. The next thing you do with the sign chart method is you draw a number line. And on this number line, you plot those 2 points that would turn this quadratic expression into 0. Now notice I drew the 1 in there. And the reason why I did, personally, you don't have to, but the reason why I plotted that 1 in the center is because honestly, this is 1 plus and minus the same wiggle. So it's symmetric, our solutions, if you will, are symmetric about the number x equals 1. I'm just going to go ahead and erase it because I think that throws people off, but I'm just letting you know that is an option to write that in there. So we have our number line. Now what do we do with that number line? Well, we're making a sign chart. And what you're going to do is you're going to go to the last inequality that you have, this guy right here, and you're going to plug in numbers in each region to see if that quadratic expression satisfies this inequality or not. For example, a number between 1 minus root 2 over 2 and 1 plus root 2 over 2, well, that's a number like 1. So if you were to try a number like 1 in your quadratic inequality, you would find out whether or not your quadratic inequality is satisfied. So here's our quadratic inequalities highlighted at the top of the screen. We're going to ask, is 0 less than or equal to, plugging in 1, 2 times 1 squared minus 4 times 1 plus 1, and that's definitely not true because that's going to be 3 minus 4 or a negative 1. So nope. We know that that quadratic expression is negative in that region, and that's not what we wanted. We wanted the quadratic inequality or the quadratic expression to be positive, greater than or equal to 0. And then you test the values in other regions. So think about a value that's in this leftmost region. Now you could grab a calculator and test it, but I'm going to tell you right now that 0 is actually in that leftmost region. So I'm going to go ahead and test x equals 0. If you go to your quadratic expression here, in fact, the entire quadratic inequality, then I'm going to ask, is 0 less than or equal to 2 times 0 squared minus 4 times 0 plus 1? Well, that's the same thing as asking, is 0 less than or equal to 1? And the answer to that is yes, it is resoundingly true that 0 is less than or equal to 1. Therefore, our quadratic expression is definitely greater than or equal to 0 in that region. In fact, for all x values, we just took an arbitrary x value, but the reality is that that quadratic expression right here would be positive for any x value less than 1 minus root 2 over 2. Let's go ahead and try the rightmost region. And just to let you know, the number 2 is actually in that region. It's a very easy number to try. And we ask ourselves, Is 0 less than or equal to 2 times 2 squared minus 4 times 2 plus 1? Well, that's the same thing as asking, is 0 less than or equal to 1? And the answer again is resoundingly yes. So this means that in that region, our quadratic expression is greater than or equal to 0, or in other words, the quadratic inequality is satisfied. And you can see the solution set, at least for this very first inequality. The solution set is going to be that highlighted interval there. Now remember, we are allowed to let x actually equal the edge points because you want that quadratic expression to be greater than or equal to. It's allowed to actually equal those edge points. So in that highlighting there, I'm going to include the edges, and we do that. Some people use a solid dot. I use a bracket. It's just a personal preference. And we could write down in interval notation, if we wanted to, the set of solutions to this specific inequality. Remember, there are two of them we have to deal with in this problem. And the interval would be written as negative infinity all the way up to 1 minus root 2 over 2, including that edge point. Skip over the stuff in between, that's what union means, and then pick back up at 1 plus root 2 over 2, including that point, and go off to infinity. So now the question is, do we do the same thing for the other quadratic inequality? And the answer is yes. If you're using the sign chart method, you do the same stuff. Focusing in on that, we'll go ahead and start by moving everything to one side. So all we did here was just subtract 5 from both sides. Now we're going to go ahead and divide both sides by 2. And we arrive at the same issue we just had, which is I know this is not going to be factorable, and so now we go ahead and use quadratic formula to set this equal to 0 and find out when this quadratic expression on the left-hand side becomes 0. And we get down to this. Our quadratic expression becomes 0 at 1 plus or minus 1/2 root 6, or root 6 over 2, however you prefer to say that. Drawing a number line and plotting our critical numbers here, we can go ahead and test points within these regions. Now our choices are going to be slightly different, not in the center. In the center, I'm still going to choose 1, but on the edges here, unfortunately 0 is not in that edge case on the left-hand side. So I'll try like -1, and on the right-hand side, I'll try +3. So let's go ahead and see what those values give us. Again, let me showcase the quadratic expression above. Start with a simple question. Is 2 times -1 squared minus 4 times -1 minus 1 less than 0? That's the same thing as asking, is 5 less than 0? And the answer to that is obviously not. So in this region, our quadratic expression is actually positive, but that's not what we want it to be. So I'm drawing that in red. To be honest, I think a lot of students do this a different way, where they just say, okay, this region, I know it's not going to be in this region. That's fine. You could totally do that. Trying the middle region. Is it the case that 2 minus 4 minus 1 is less than 0? Or in other words, is -3 less than 0? And the answer is yes. And then finally, trying the rightmost region. Is 2 times 3 squared minus 4 times 3 minus 1 less than 0? And the answer to that is absolutely not. That'd be 18 minus 13, which is 5, and that is definitely not less than 0. So we can say this region is not part of our solution set. So the solution set to this specific quadratic inequality is that highlighted region right there. And remember, this time the inequality, we cannot include the edge points because we want our inequality to be strict. So let's go ahead and note that. I use parentheses. Again, you could use open circles. Everybody's a little bit different. And now we're going to combine up those two highlighted regions on those intervals to get our actual solution set to our original compound inequality here. To do that, it is pretty beneficial to figure out what those numbers on those intervals are. For example, 1 minus root 2 over 2. That is roughly 0.3. And a 1 plus root 2 over 2 is roughly, again, 1.7. Also, we'll need to find out what these values on these edge points here are. 1 minus root 6 over 2 is approximately, not exactly, 0.2. And a 1 plus root 6 over 2, again, it's very approximately 2.2. That will help us out quite a bit. So notice our highlighting starts with negative infinity, just point at that, all the way up to 0.3. However, this highlighting starts at 0.2. So if you overlap those two highlights, and in fact, you know what? I'll go ahead and actually physically overlap these highlights. So here we go. I kind of copied and kind of adjusted a little bit, but that's the relative placements of those values. And notice where they overlap, pretty much in those regions right there. So let's go ahead and write in interval notation what that overlap is. Starting with the leftmost edge, starts at 1 minus a root 6 over 2. We're not going to include that. That highlighting will climb all the way up until you get to 1 minus root 2 over 2. You get to include that. And then you're going to skip over the whole central region because there's not a double highlighting there. You're going to pick back up right here at 1 plus a root 2 over 2, and then continue onward until you get to 1 plus a root 6 over 2. And you're not going to include that edge point. That is the solution set to this quadratic inequality. Now, all of that work to then say there's yet another way to have done this. I'm going to go ahead and circle this up because otherwise it'll be hard for me to see on the screen. The second method you could have used here to solve this quadratic inequality, the original compound one there up above, is to graph both of those quadratics. When I say both of those quadratics, I really mean this quadratic right here, which is highlighted, and this quadratic right here. In reality, a lot of students dislike graphing, but it's a good skill to keep at hand. So in both cases, you would do essentially the same amount of work. You'd start by breaking this compound inequality into its two component pieces, which we did in the first method. Then you would isolate or remove the entire quadratic expression to one side, again, in both cases. So up to this point, it's the same amount of work as the sign chart method. You would also find the x-intercepts. And when I say the x-intercepts, I really mean that you're going to graph these quadratic equations or the quadratic expressions that are on the single sides of these inequalities. For example, on this inequality right here, you're going to graph 2x squared minus 4x plus 1. On the other inequality right over here, you're going to graph 2x squared minus 4x minus 1. But to graph that accurately, you would need your x-intercepts, which requires using the quadratic formula, which we did. So again, in both cases, method 1, which uses sign charts, and method 2, which uses graphing, you're doing the same amount of work up to this point. But that is it. When we use sign charts, we had a lot of extra work we had to do. But when you're using graphing, I know that, for an example, the first parabola we're graphing, which is 2x squared minus 4x plus 1, it opens upward because the lead coefficient is positive. And I have x-intercepts of 1 plus or minus root 2 over 2. So let me plot those here. And I happen to know the parabola opens upward. I don't need really anything else here. I just need to know kind of the basic shape. And we're asking ourselves in this instance, when is that parabola right there above the x-axis? Let me write that down. And you can easily see that on this graph. It's all this stuff right here. Notice this is the same interval I had when I had to do all the mechanical mathematics for the sign chart. A lot of students love the sign chart because they dislike graphing, but the reality is I didn't have to do any extra work to do the graphing method. In fact, I had to do less work. The only thing I had to remember is if the lead coefficient is positive, my parabola opens up. And I guess the other thing I had to remember is that really this inequality sign right here is telling us we want our parabola to be above a height of 0, or at or above a height of 0. So I'll mark that at or above the height of 0 on our graph here. So these are all the x values that satisfy the condition that our parabola be at or above a height of 0. We do the same thing with the second quadratic inequality. This guy right here, I'm going to graph 2x squared minus 4x minus 1. I want that graph to be below the height of 0. So again, we found our x-intercepts. I will plot those very quickly. It doesn't have to be super awesome. And we happen to know that the parabola that we're about to graph opens upward because that's a positive 2. And again, we want to know when is the parabola below a height of 0. So here's my parabola that opens up. I don't really care about where the vertex is. That's not a concern. I just want to know for what x values is that parabola below the x-axis or below a height of 0. And you can see it's all of these x values right there, going from 1 minus root 6 over 2 all the way up to 1 plus a root 6 over 2. Notice mechanically much less work with graphing. And then you find the intersection of those two intervals. It will still be this same stuff right here. So that's just a heads up. The graphing method is a really good method to use when solving quadratic inequalities and actually rational inequalities, which will be the next video. I hope this sparked some creativity for you. I hope this reminded you how to solve inequalities, nonlinear inequalities, and I'll see you in the next video to solve a rational inequality.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine, just